Let us now talk about recursive C++ implementation for BST insert. So first case is very clear. If root is empty, then we create a new node with the value x and we return this new node, right? If the root arrow key is smaller than x, the key that we want to insert, x, if it's greater, then this key is definitely going to be inserted into the right subtree, right? So we recursively call for the right subtree. And this is where many people make mistake when they write insert themselves. They do not write this part. They simply return insert. We'll see with a dry run that simply returning insert would not work. If root arrow key is greater than x, then we know that x has to be inserted into the left subtree because root is greater. So you insert into the left subtree and whatever new root you get after the insertion, you make it as root arrow left. At the end, we return root. Let's now understand what is the meaning of assigning the return value back to right and assigning the return value back to left. Let's see how does this return value work in the recursion. So we have 20 to be inserted. If we dry run this code, we are going to come here with this root and this value 20. We will not go into the if part because root is not null. Root is pointing to this node. We'll come here, right, inside this part because the value that we want to insert 20 is greater than 10. So we come here and we recursively call insert with this root, right, this new root and x equal to 20. Right, x is going to be 20 throughout the calls, but this is your new root. Now you begin your execution for this node and this node is again not null. And this node is again smaller, so you will call for the right of this node. So you now call for this node, 18. Now you again begin your execution with this node. It's not null, so you will not go here. You will come here and you will again call for the right. And right of this is null. So you pass this null as a parameter into the right call and you pass x equal to 20. When you come here, what happens? You enter into the base case when your root is null. So what do? You allocate a new node, right? You allocate a new node with value 20. But just allocation and returning does not link these two nodes, right? We need to link this right child back to 18. We need to make this new node as right child of 18. That is why we have this assignment. So this function call that we initially called for null, it returned a new root with value 20 and now this returned pointer is assigned as a right of 18 and this is where this linking happens, This is where this linking happens. This is linked with this root. Now when this calls to this parent, it's going to override the same value. This is anyways right and it's going to tell, okay, I'm now your new right. And this is going to again override this right pointer. So this is how this insertion work. This is how we do insertion using recursion. Let us now talk about iterative insert. Iterative code is slightly longer. The reason is we need to have hold of the parent node also. Let us understand why. Like normal BST search, we are going to do a BST search, then we are going to end up in a null and that is where we are going to insert. Suppose we want to insert 20 here, we'll begin from here, we'll know that it has to be inserted in the right side, we'll come here. We know it has to be inserted in the right side, so we come here and then we insert here, right? That we know for sure. Now when I'm inserting a node here, my current is null, but how do I connect the parent of this new position with this new node, right? We need to make this connection also. For that purpose, we maintain an extra pointer called parent, right? So we run the simple search loop where current begins with root and it goes left on right accordingly, right? If it is greater, then goes to the left. If it is smaller, then goes to the right. If it's same, then you don't need to insert this new value and you simply return the old root, right? So you keep doing it. While doing it, you also maintain the parent pointer. Before you move current to one of its children, you make parent updated, right, to the value of previous current. After you come out of this loop, your current would definitely be null, right? And your parent pointer will have the pointer to the parent. Suppose you are inserting 20 here, then parent will be here and your current will be null, right? This particular condition is exceptional condition to handle the case when somebody gives you an empty tree, because in this case parent will never be updated and it will remain null, right? So this condition is only for that particular case. In this case, in most of the other cases, our parent will be here, right, after this loop. And now what are we doing? We are simply checking if parent arrow key is greater than x, then make it a left child. If it is smaller, make it a right child. So you already have a newly allocated node here in the beginning of this code, which is your temp node, right? You have this node with the value 20. You only wanted to make a connection between 18 and 20. And for this, we have all done all this work. We began from root, came here. We have the parent pointer to this node. Now we are going to make parent arrow right equal to 10 because parent key is smaller than 20. That's all we'll do. And at the end, we'll return root. So this is iterative insert for BST. Let us now do time complexity analysis and auxiliary space analysis of both iterative and recursive inserts. Like binary search tree search function, this insert function also does the search. It does one extra work of creating a new node and connecting the node. Otherwise, time complexity and auxiliary space complexity requirements are same as search. And we discussed in the search, if you're doing recursive insert, then your time complexity is big O of h, where h is the height of this tree. And auxiliary space in the recursion is big O of h. If you're doing iterative insert, then your time complexity is same as recursive, it's big O of h, but auxiliary space now is big O of 1. So your iterative is generally better because it does not require that big O of h extra space. Also, it does not cause that overhead of making recursive function calls.